It just takes a while to connect. Hopefully everything it can handle, connecting up with all three devices. It just takes a while to connect. Okay, so hopefully everything it can handle. Here we are. Unfortunately, there's a real weird delay. Devices. Mute that. All right. Okay, so it looks like we got page 35, number 26, and then we'll have a quiz right afterwards. And the quiz is on basically last week and this week. So this week's material is not that, the homework isn't that relevant that you asked, but let's do it quickly anyway. Then we'll have the quiz. Let's see, 35. Page 35, number 26. Okay, I guess I'll do it down here. And so it says approximate numerically this limit. This is just another approach to finding the answer to these limits. And so we're trying to find this limit. And so this limit right here, this thing is approximately equal to the value. Well, let's see. Let me back that up and say that this is equal to the limit as x goes to 0.2 of f of x, where f of x is this value. Okay, and so when I want to find what's happening in that, I want to know what does f of x get closer and closer to as the x value gets closer and closer to 0.2. So one way to figure that out is to just stick in a number that's close to 0.2. So when they say approximate this numerically, I'm just going to stick in f of 0.2001. And so one way to do it is to just figure out what is f of 0.2? Well, not exactly 0.2, because f of 0.2 is probably undefined. Or else the problem is very easy. I would just figure it out, and then that's the limit. So is it undefined? I don't know. If I stick it in, the value 0.2, then I'm going to get 0.2 squared is 0.004. No, wait, let's see, I'm sorry. It's been a while since I've had to do arithmetic in my head. So it's 0.04 plus 5.48, 5.8 times 0.2 minus 1.2, all divided by 0.04 minus 4.2 times 0.2 plus 0.8. And so we do that arithmetic, right? And so I have to do 0.04. I have to do plus 0.1. What is that? 58 is 116. Like that. Minus 1.2. Oh, is this not going to give me? I don't know. I should have been using a calculator on this thing, right? Since I can't do arithmetic in my head that well. So we have 0.84 plus 0.8.
Anybody have any improvements on that?
It's 1.16.
Oh, 1.16? Yeah, thank you. Good catch. That should be right there. 1.16. Yep. That will make it better. 1.16 plus 1 0.04 is 1.2, minus 1.2 is 0 on the top, and minus 0.84 plus 0.8 is minus 0.04, plus 0.04 is 0 over 0. So you see, yeah, sure enough, as I guessed, it was undefined. So you can't estimate what the limit is by sticking in the numerical value of 0.2. You get a nonsensical answer. That doesn't give us an answer of what this is getting closer and closer to. It's undefined there. So this function is going to have a hole in it at some point. Roughly, this is what the function's graph is going to look like. I don't know what the shape is going to look like, but at 0.2, there's going to be a hole. And so that's why it looks like it's undefined there. Everywhere else it's defined, well, except the two places where you divide by 0. It's going to shoot off to infinity on the other one. So this is square. And so since it has 1 0 at 0.2, there's going to be another 0 somewhere because it's a quadratic polynomial. So it has 2 roots. Anyway, so there's 2 spots where it's going to be 0. So it doesn't matter, though. What we're actually concerned with is how do I approximate the value numerically. Now, the right way to do it is analytically, is actually to factor it out and find the 2 different values where there's roots and simplify it after you take out the x minus 0.2 from here and factor that out, and x minus 0.2 on the top, factor those out, cancel them, and then you can stick in 0.2 into the remaining piece, and it should work. But that's not what we're going to do. It asked us to approximate the limit. So following the directions, approximate the limit numerically, we're going to not find out what the limit is exactly equal to, but I'm going to find out what the limit is approximately equal to. And it's going to be approximately equal to f of 0.2001. Okay, that number is close to 0.2. Okay, and I'm just making that up right now. I'm just picking a number that's very close to 0.2. So 0.2 is what I really want, is when x actually goes exactly to 0.2, but I can't stick in exactly 0.2 and just into the function. But I can calculate what the limit is going to be exactly in all of these cases. So what I do is I stick in a number close to it, is how I approximate it. Again, that's not how I find the exact answer, but it will give me a hint about how to do the exact answer. This is an engineering answer. It's a good way to do it. Calculator will just tell us the answer. Or even better, it's even more approximately equal to f of 0.20000001. Okay, that's a better estimate for what the limit is actually going to be, and you'll be able to guess what the limit is going to be after you check this one and check this one. Now, I'm not going to do that. I don't even have a calculator with me, but what I'm saying is I'm just going to stick this 2.001 here, 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 and here, right? I stick those in, and I get the estimate for what the limit is going to be. Okay, the limit as x approaches 0.2 of f of x, because this is a number that's approaching 0.2. The 0.001 is really close to 0.2, and that's it. Okay, so I won't show you the whole thing, but I'm just going to put in 0.2001. You square it. You put plus 5.8 times 0.2001 minus 1.2. And that number won't be 0, right? Here, when I put in exactly 0.2 here, then I got this answer of 0 on the top. And so I won't get 0 when I put something nearby the 0. Okay, and also I have to put it in the bottom. I have to square 0.2001 and minus 4.2 times 0.2001 and add 0.8. I'll just write that out, but I'm not actually going to stick it in a calculator. And I could figure out what this is. If you want me to guess real quick, Well, no, okay. I mean, I don't want to show you a trick. Later, we're going to learn a trick for simplifying this quite a bit called L'Hopital's rule, and it makes this whole calculation a lot easier. You just take the derivative of the top and the derivative of the bottom, but we haven't learned how to take derivatives yet, so I don't want to confuse anybody yet. So this is going to be easier later, but right now, stick it in a calculator. Equals, I don't know. Did anybody get an estimate for that? Anybody want to help me out?
I have a question.
Negative 1.63.
Okay. Somebody claims that. Anybody want to back her up? Everybody agree with that?
I got that answer as well,
Awesome.
but I tried factoring it.
Uh-huh.
Is that something you're able to do, or do you have to do it this way?
That's what you're supposed to do every other time. But this is asking a weird question for review that you're supposed to find the limit numerically. So that key thing is, no, you need to follow the directions in this case. But no, that in real life, you're not forced to do any particular way to approach it. It's just for the purposes of the homework problem. So yeah, absolutely. Factoring it is a better way from a mathematician's perspective. But to be honest, like an engineer might appreciate this a little bit better because you can stick it in a calculator and you're done. It's not as good for a mathematician because the answer is approximate. And I don't know it's minus 1.63. I don't know how many decimals are correct. It might be exactly correct, but if you are sticking it in a calculator, you never know you've got the perfect answer. That's why if you can find an analytic answer, and that's the difference between numerical answer versus what's called analytic. What analytic means is just you think about it. Okay, if you just do it in your head, like you do it with a piece of paper and you think about it and you figure out the answer. And what it really means is Greek for loosen, to piece it apart and break down the problem and figure it into more simple basics. And that's what half of all mathematics is analysis.
I had a question. Could you just use the store function on your calculator and store like 0.1999 and then solve it that way?
Yeah, exactly. Yeah, please, exactly. However tricks you know on your calculator, that's what we're asking for. Yeah, you want to put the store 0.199 or 0.2001. So instead of approximate with that, it's also approximately equal to f of 0.1999. Right, that's close to 0.2 as well. So another good point there. All good points. Any other questions or comments about that one? Okay, well, that's it for that section. Again, interrupt me. I'm happy to do more. We're going to be done real super quick. Then you'll be able to do your quiz. But the other one that I saw was page 44, number 35.
Someone in the chat also asked for number 22.
22. Okay. Again, please use the Google Docs. Does anybody want me to show you how to do the Google Docs one? It just makes it a lot easier and it'll be more efficient if I don't have to beg for homework problems at this point. I'll just do a whole bunch of them. But yeah, I'll do number 22 because we only have 3 then. And again, I can't see the chat while I'm working on the iPad. Okay, so number 22, determine if f is continuous at the indicated values. If not, explain why. Okay, so now we're supposed to do number 22. And is this function continuous at 0 and at 8? Okay, at 0, so let me write it because it's a little small. Well, maybe you can see it on the computer. If I look at this thing, so f of 0 is in the top value. So when I'm looking for x equals 0, I just put in f of 0, and that means, well, when x is not equal to 8, then this is the formula. And for x nearby 0, which is also not equal to 8, this is the formula. So if I stick in 0 here for these, I just get 0 squared minus 64. over 0 squared minus 0 plus 24. And so the value at 0 is minus 64 over 24. I just get a fine answer there. We could simplify that by factoring out what we have a 4. No, we actually have an 8 in common. So I get minus 8 over 3. Okay, and there's no problem. So one of the theorems in the section talked about, as long as the function is continuous at the spot, you can combine the continuous things. So basically, if I'm not dividing by 0 in a rational function, then the function is continuous. And so it's going to have the limit as x approaches 0 equal to that value. So no problem. When I stick it in, I don't get divided by 0, so it's continuous. So yes to part A. Now part B is a lot harder. So let's take some space to do that one. I have x squared minus 64. I don't know if I can lasso select this thing. Let's see. I have my doubts. Oh, well, it didn't do a good job. Yeah, it's not liking it. No. Okay, the part I actually want is just this piece. Yeah, it doesn't like that. Okay, so I have to just recopy this thing over here and say, so for number 22, we're looking at f of x is equal to 5 or x squared minus 64 divided by x squared minus 11x plus 24. And that's for x not equal to 8 and at x equals 8. And the question is f continuous at x equals 8? So in other words, the limit as f approaches 8, that's for these values when it's not equal to 8 but is approaching 8, is the f value for the formula here, is that getting closer and closer to the value of f when it's equal to 8? When it's equal to 8, it's 5. So that's the same as asking the question. This is equivalent sign. That's equivalent to asking is geez, the limit as f approaches jeez. Oh yeah, this software is just killing me. That's the same question from a mathematical point of view. If I ask, this is the definition of continuity at a point, is whether or not the limit as x approaches 8 equal to f of 8. And so I just have to calculate that limit. And so let's do it. And that's the same thing as asking, what's the limit as x approaches 8 of x squared minus 64, all divided by x squared minus 11x plus 24. Because that's what f of x is equal to when x is not equal to 8, but nearby 8. And that's what the limit is asking. And so when I look nearby 8, but not equal to 8, that's this part, right? That's that formula. Okay, and that's the same thing as the limit as x approaches 8. Well, I already stuck in x equals 8. On the top, I'd get 0. So I'm not going to write out the extra piece up here. I'm just going to check real quick because I get 0 for x squared, or 64 for x squared minus 64, and then 64 minus 88 plus 24 is going to be 0. Okay, and so 0 over 0 is the form of this limit. That's not the answer to the limit. So the answer is never 0 over 0. It's just the structure that's going to be, which is a sort of a, okay, this is the type of confusion we have. We don't know what the limit as x approaches 8, because 0 over 0 is not a good answer. So I need to do something different. And in the case with these rational functions, it's always one trick. And so it's going to be a trick that's going to show up on your quizzes and on your midterm. So good question. That was added at the last minute. Good job, whoever did that. I need to factor it. And that's how you factor the top, because 8's a perfect square. And factor the bottom. It has an 8 in it, we checked, because we got 0 on the bottom. So x minus 8, when I stick in 8, if I get 0, it means x minus 8 must be one of the factors. And so the other piece is just a 3, right? That 8 times 3 is 24, and it needs to be both minuses if you're going to make a positive 24, and they work out that it'll be minus 8x and minus 3x is minus 11x. Okay, so that's our factorization. And now if we look at that, we notice that this simplifies. For values of x not equal to 8, they cancel. I can cancel that. When x is close to 8, like 7.99 minus 8 divided by 7.99 minus 8, those two numbers will cancel. No matter what x I have, as long as x is not equal to 8. So now, what's the limit of this simplified rational function? It's a lot simpler, and it's just 8 plus 8 over 8 minus 3. And that one doesn't have a problem, so 16 over 5 is the answer. And so is the limit, so is that our answer? We're done? No, our question was, is f continuous at 8? And so in other words, was the limit as x approaches 8 of f of x equal to f of 8? Well, our limit was 16/5. That's not the same thing as 5, which is what f of 8 is. So therefore, it's not continuous, or it's discontinuous. And that's the right answer. With that justification, you need to show me that the limit is, you need to find out what that limit is. You need to find the limit, check whether it's equal to f of 8. And if it is equal, then they're continuous, then the function is continuous at that spot. And if it's not equal, then they're discontinuous. Any questions about that one before we head on to another one? Okay, it says do page 44, number 35. Okay, so this one right here. So it's a test of the intermediate value theorem. And so it says, let's say that f is continuous on the interval from 1 to 5. So you're here from 1 to 5. That's a bad example of 1 to 5, right? Okay. And so graphing this thing from 1 to 5, something like that. So it's continuous there. You know that f of 1 is minus 2, and f of 5 is minus 10. Okay, so I'm going to put minus 2 here, so I can fit minus 10 here. And so they say f of 5 is minus 10. So that's what f of 5 is. And this is f of 1. So now my function f here, it has to be continuous. So now I don't know what it looks like. The function will look, it's going to connect up those 2 points in some way. So it could look like this. I'm just taking a long time to connect with Facebook and rather Google or yeah, YouTube. Geez, it's really
Sucking here.
not changing the color. Or it could look like this. I mean, I don't know what the function is going to look like, but I do know it's going to be continuous. And so the question is this function necessarily going to hit some value is going to hit -9? In other words, is it going to hit this spot right here? Jeez. And so is it going to hit that spot? In other words, is there some place it's going to hit that's right at that spot? Okay. And so sure enough, no matter whether you're on the green line or on the red line, if it's a continuous function, it has to run across that, that purple line. So those green curves or the red curve has to cross over that purple line where f is equal to -9. And so the answer is yes. By the intermediate value theorem, that's the thinking that goes along. Yes, there exists a c in 1 to there exists a c in 1 to 5 such that f of c is equal to -9. And that's all the technical way to describe it. But that's what this is a theorem. It's all theoretical. So that's why I'm throwing in these hardcore symbols of there exists a c inside the set between 1 and 5 such that all this stuff. Okay. And just as a hint, that's on your homework, but it's not necessarily on a big thing that I'm going to focus on for the midterm or the final. Okay, any other questions or comments about anything before we do our quiz?
Page 44, 26.
Okay. 44, number 26. Okay. So tell where this function is continuous. And the key for this is that theorem that says these basic functions where we use the formulas that we always use in math classes are continuous wherever they're defined. Okay, so whenever you have basic functions, that's the case. By basic functions, I mean all the algebraic functions, which all of these are, just have square roots and squares and fractions. All of them are rational, or sorry, all of them are algebraic functions, except for this last one, which is exponential. And so they're all continuous wherever they're defined. Now, it turns out that this is for math class, okay? The hardcore math that you will actually use, maybe you won't use the hardcore math, okay? But if you're going to use math for serious modeling purposes, what often happens is you're using a computer to approximate some process. And then you start ending up using, well, you need calculus to use much more complicated functions. And so there are more complicated functions than these, and you'll learn about those in Calculus 2. At the end of Calculus 2, when we do Taylor's theorem, is the beginning of a whole new universe of functions where you can describe any function you want that does anything at all. And so that's the coolest thing about Calculus 2. But for these ones, these are all like practice functions in the world. Now, these infinitely complicated ones that are way more difficult, they're just built up out of basic functions. So if you understand the basic functions, you're ready to go after calculus to do all possible functions, anything you can possibly write down, whether it has discontinuities or not. There's enormous power in how you approximate them with other basic simple functions. So this is the understanding for how to figure out all applied math afterwards, is after you get through Calculus 2. But for us, let's get through this one, which is find out whether or not where this thing is continuous, and we just have to find out where it's defined. And so the problem with square root function is square root of x is domain is for x greater than 0, it's good to go. And it's also good at 0. Okay, and I'm not going to care whether or not you call it continuous at 0 or continuous or not continuous at 0. But just because it's defined here and then it sort of stops right there, it's fine. Some books say that's continuous there, some say it's not. And I don't care about that. I won't ask you about that. Meaning I won't, whichever answer you give me at the end point is fine. Okay, so, but these guys are not just the square root of x, it's h of k is the square root of 1 minus k and square root of k plus 1. So what are the k's that I can stick in? I basically want to know what's the domain of this function. And it's the k's that you can stick in. And so which k's can I stick in? And it's the k's that are, well, I can't have a negative value in here. And so basically, k has to be bigger than minus 1. Or else, when I stick it into this second square root, then I'm going to get a negative value. So if I put in minus 2, I'll get minus 2 plus 1 is minus 1. I take the square root, and I'll be in trouble. Square root of minus 1 is imaginary, so we jumped out of the subject where we're talking about. We're not going to do calculus with I in this class. So it's very easy to do it, actually. It's just like, well, let's learn it with some basic one-dimensional calculus first. Turns out calculus gets easier when you start using imaginary numbers. So that's why we do it. That's why physicists really like doing it. Anyway, but we're not, it's like just theoretically weirder, right? So we're not going to discuss that until you've had calculus for a couple of years. Okay, and then the second part is this thing has to be greater than 0 if I'm going to stick a number in here. And so I can't pick a number k that's bigger than 1. If I can't pick a k number that's 2 or 10, then this is going to have trouble. So I need to make sure that 1 minus k is greater than 0. So the answer is k is greater than 2. Sorry, k is greater than 1. Sorry, no, k is less than, it can't be any bigger than 1, right? Okay, so that's the way I just intuitively just do it. And that's how the physicists do it, okay? But that's not how the mathematicians want you to do it. The mathematicians want you to just find a process that's going to work on that. So what you need to do is just write down the algebra of that. This is the answer, by the way. I'm finished there if you want. That k is bigger than minus 1 and smaller than 1. But another way to do it, yeah, go ahead.
Why can't it be greater than or equal to -1? Because you put in -1, like 1 minus -1, or 1 minus 1, that'd be 0, and you can get the square root of 0. So why can't it be equal to?
You're exactly right. I'm wrong. It should be greater than or equal to and less than or equal to. Both of those are good. And that's life, okay? So I'm going to make tons of mistakes, and I'm happy to make mistakes. I'm happy to display mistakes for you. That's how you do math. That's why you need erasers on your pencils, and don't use a pen when you're doing math. It's just a monstrous thing to do, and my daughter does it anyway. It really drives me nuts. But anyway.
I have a question. Could you use brackets and say -1, comma 1, both in brackets, or is that, I mean, I had basically the greater than and equal to and all that, but I use notations and use brackets.
Yeah, that's exactly right. Good comment. That's also the right answer. Any k in this bracket right here, this means between -1 and 1. And that's numbers that are both greater than -1, greater than or equal to -1 because of the square bracket, and less than or equal to 1 is what this is true. So I really want an and on that, right?
I'm sorry. Why wouldn't anything greater than -1 work?
Anything greater than -1. So if you want to put in 2, for instance, right? Is 2 any good? Well, if I stick a 2 in for k, then the first one has a problem, right? If 1 minus 2 is -1 and I take the square root, it's a problem.
Oh yeah, I was thinking only half of it.
Yeah. So let's do it a little slower. Do it the mathy way, the math teachers like. is just, here's the way you're supposed to do it. Here's the way you're supposed to analyze it. Okay, again, that word analysis comes in, is that we want the square root of x has to be for x greater than or equal to 0, right, is the domain. Well, then if I have the square root of 1 minus k, then 1 minus k has to be greater than or equal to 0. And that's the same thing as 1 is greater than or equal to k, and that's this one, this bottom one. And then the second part, I want the square root of k plus 1. Well, if it's going to be in that domain also, I need k plus 1 to be greater than or equal to 0. And that's equivalent to saying that k is greater than or equal to minus 1. So I need both of those to be true, this one and that one true. So I need that one and that one to be true. K is greater than or equal to minus 1 is the second one that I mentioned up there. So that's a slow way to do it, but that's not the way the physicists do it. And this class is really a physics engineering class, right? Computer science, that sort of thing. And so they are just much more interested in what's the answer, and there's the answer. And that's why physicists are better at mathematicians at doing math on most problems. But they're not too good at inventing brand new math. And the reason is just that they don't really know what the rules are. So they have to live with what they were taught a little bit more. Okay, so if physicists want to really invent their new math to discover their new theories, they have to really go back and think about what the math means before they can do it. So they have to become mathematicians, and they have to think about it like mathematicians. So super rare, it's not that needed. So this class is for the engineers and people who just want a good answer real quick and dirty. So it's good to do it both ways, but I'm only in this class demanding that you just know how to do the answer real quick. And then again, if you take Math 301, then we'll go back to basics and think about the whys behind things very, very carefully. Okay, any comments or questions about that? Okay, and is that all the questions? Any other questions wanted? Okay, well, I'm gonna stop the